Okay, so today, like I said last week, was a lecture sort of linking the two halves of the module. So at the beginning of the module, we did a sort of a bit of a crash course which covered some revision for some people and some new stuff for other people. And then we sort of moved into talking about the linear model, but in the context really of how it's used to sort of deal with correlational data. The second half of the module, so basically everything from now until Christmas, I'd say in a way that I think the pace of the module slows down quite a bit now, you'll probably be pleased to know, because we're mainly dealing with sort of experimental designs and how to analyse them. And really what we're doing is, what I'm hoping that last week's lecture and this week's lecture will show you, is that we're not doing anything particularly different to what we've already covered in the module. So we're really just going over old themes again and again and again. So hopefully, so if there are things you haven't understood at the beginning, hopefully by the end of the module you will get them, because we just literally keep going over and over sort of the same ground but in slightly different contexts. So I guess that's also a way of saying if you didn't do so well on the exercise, don't panic, because a lot of the stuff that we've already gone over we kind of come back to again and again and again. So it will sink in. Which, by that you may have guessed, I've seen a bit of the results, and some were better than others. But anyway, some people did really well. I'm trying to focus on that. So what we're going to do today is to have a look at how the linear model is used in the context of experimental designs. And really, that means it's kind of a lecture about ANOVA. We've already actually encountered ANOVA. When you've been looking at your regression outputs, you will have seen, hopefully, a table at the top of which it says ANOVA. And a few lectures ago, I mentioned an F statistic and what that's used for in the context of sort of correlational research. So we're now moving on to look at sort of experimental designs and how the ANOVA is used in that context. But really, like I say, hopefully this lecture is about how things are not too different to what we've already done. So last week's linking lecture was a bit to kind of show you that you can look at differences between means using a linear model, and the linear model is versatile enough to deal with that. In this week's lecture, we're going to deal specifically with sort of applying that to experimental designs. We're going to have a look. This is why it's not the most fun lecture. We have a look at how the F ratio is actually computed, and there are some equations bandied around. That's not particularly what I want you to focus on. I kind of think it's important to explain them in this lecture, but it's not the main thing. The main thing is that you have a conceptual understanding of what sums of squares, mean squares, and what the F ratio actually represents. And that's why the equations are in there, to try and give you that conceptual understanding. But I also do it a lot with diagrams and things like that as well. But in terms of actual number crunching, when it comes to your practical class and things like that, you won't be going through lots of equations, but I do want you to come out of this, and certainly in terms of the end of module exam, I want people to understand what a sum of squares, a mean squares, and an F ratio is, and what the relationship between those things are. So how you would compute a mean square from a sum of squares, and so on and so forth. How you would compute an F ratio from means and sums of squares. So just bear that in mind. So experimental designs, you can, basically we use them to try and get at causality. So we covered this a bit when we did the introduction to your lab report. So the idea behind them is that rather than correlational research, where we just measure variables that are sort of naturally occurring, in experimental designs we manipulate things to look at whether that manipulation has a specific effect on something. And through doing that manipulation, if you do your control groups properly, you can get a cause and effect. So the idea is you manipulate them in such a way that some participants have the causal agent present, whatever it is you think is having a causal effect, and other participants in the control group will not have that causal agent. And because you've systematically manipulated what happens to, say, the two or more groups, you can draw firm conclusions that any differences that you get between those groups are down to what you've done. So, for example, take a very simple example. There's lots of... I do periodically use the gym up at the Falmouth Sports Complex, and normally they have a desk as you go in, and on that desk are lots of fitness magazines, and I always find them slightly I don't find them motivating. I just find them depressing because they normally have images like, I don't know if my pen thinks, yeah, they normally have images like that on the front page. And at my age, well, in fact, I don't think even if I was 20, that's an unattainable goal for me. I think I can safely say there's no point in my life where I'm ever going to look like that. And I'm not sure I'd even want to, but I might want to just a little bit. My wife might want me to. Who knows? But it's depressing, frankly. And I think if they put something like this on the front of magazines, I would find it a bit more motivating. I think that's something I can achieve by not even necessarily by coming to the gym. So the point is, what impact do these magazines have? Now, women have been subjected to this crap for a lot longer than men. These ridiculous images of stick-thin people in magazines. And now, finally, we're getting a bit of a dose of our own medicine with these kind of fitness magazines. So we might want to look at what the effect of this is. Now, our causal agent the effect on, say, something like self-esteem. So our causal agent is the magazines or the images in the media. And that's what we're sort of predicting is having an impact on our self-esteem, and we're presuming that it will lower it to some extent. So the manipulation we would want to do in an ideal world is to have a group of people who we expose lots and lots to these kinds of magazines or media images, and then have a control group of people who we somehow manage to protect from them in some kind of way. Now, obviously, it's not a perfect world, and people will see these images anyway, but that's ideally what we would do. We would completely isolate those groups. Now, if we randomize people to those groups, then that means that we can sort of assume, on balance, those groups are pretty equal. Now, randomization doesn't guarantee that they're going to be sort of equal, but the whole point is, on balance, on average, you should get groups who are sort of similar in their IQs and other sort of variables, the amount they go to the gym or the amount they give a shit about what they look like, that sort of thing. So, what we'd be hoping would happen is we've randomly selected some people. So we've got a population of people that we could select from, and if we were to take we've seen this diagram possibly more than once before. If we took random samples from this population, so any one of these, they'll represent that population to a lesser or greater degree. But on average, they should basically be the same. So if the mean in the population is, say, 3, the sample mean might be 3, or it might be slightly different, might be 4, but it's not going to vary too much. So other things being equal, if we took 2 groups of people and we randomly assigned them, and we didn't expose them to magazines, then we'd expect their self-esteem scores to be pretty similar. Not necessarily identical, but pretty similar. If we've randomized them, they should more or less, on balance, be the same. If we exposed one of the groups to these magazines or images or whatever, then what we'd expect, if and only if the magazines have an effect on their self-esteem, is that it might, for example, lower in that group. So the difference between the samples that we've got is not due to the fact that we happen to have taken 2 different samples, because randomization should make sure that those samples ought to be, on balance, pretty equal. So if there is sort of a difference between them, it ought to be down to the fact that we've manipulated something. We've systematically done something to one group that we haven't done to the other. So we've kind of gone over this a bit before, but I'm just reminding you, this is the sort of whole point of experiments. We manipulate variables, we don't measure them in a sort of naturalistic way. Now, in terms of sort of fitting a model to check whether that manipulation has worked, what we're really wanting to do is to fit a model to the data that compares the means of those groups. So it's actually looking at kind of the difference between those 2 means. Now, this is all well and good, and we kind of looked at this last week. We looked at the African and Asian elephants playing football, and we saw that it's reasonably straightforward to fit a model to the data, a linear model, same kind of model that we've fitted through the whole of this module, to compare the differences between those 2 means. That's all fine. We've seen how that works. But in reality, we quite often have situations where we want to look at more than 2 conditions. So, as you'll see as the module goes on, experimental designs can get increasingly complicated. So let's look at another example. What about the amount of injury that different animals can, or different pets can inflict on their owners. Now, this is a particularly pertinent example to me because I have a cat. He's a very old cat these days. There he is. He's called Fuzzy. Didn't think that through terribly well when I named him, but he's now been stuck with it for 16 years, and he's huge. He's the king of the garden. Well, he was. He's a bit old now, but he's a really big, robust ginger Tom, and he's got a name called Fuzzy. You can just imagine him walking around the gardens and all the other cats going, "Oh, what's your name?" Because that's how cats talk, and him going, "My name is Lord Fuzzy, the Impaler of all other cats." And they're like, "Your name's just Fuzzy, isn't it?" Yes. But nevertheless, he's quite sweet. Where he's not sweet is he really likes to sit on my lap, which is quite sweet in itself. He's a bit of a he's blatantly my surrogate child. So he likes to sit on my lap. But one unpleasant thing about when he does like to sit on my lap is he likes to claw my testicles. And trust me, there's nothing special about my testicles. They're just everyday kind of testicles that your average person has. But for some reason, he really likes them. He really likes them a lot, and he sits on my lap and he does that thing, and you can look, claws. Look at them; they're huge. And he'll be doing that, and I'll be like, "Oh, don't do that." And this gets me thinking about pets and injuries and stuff like that. So I sometimes think, would I have been better off getting a dog, for example? Would I suffer less personal injury if I had a dog? Now, dogs, they don't tend to claw my testicles on a day-to-day basis. Quite a lot of them sniff them. Like I say, they're just ordinary testicles. I don't know why. I don't think they are particularly fragrant. I hope they're not particularly fragrant. But nevertheless, dogs seem inexplicably attracted to them. This may be a general thing, or it may be specific to me. I'm not sure. So I kind of think, could get bitten there, really. I don't really like it when a dog runs up to you and kind of pokes its face in your testicles. It's a bit embarrassing. And I do kind of think, what if they just think, I'll have a bite? I don't generally wear chainmail under my trousers, so that wouldn't be very pleasant. So I think, maybe a dog's not the right thing to get. Maybe I should get like a bird or something. I think birds are probably pretty safe. Not massively into the idea of keeping birds in cages, but maybe I could have it flying around the house. But then, who knows? Because birds like worms and things like that. Maybe it's got some kind of homing beacon on wormy type things, and it will come and peck my testicles. I don't know. But if I wanted to test this systematically, there was a point to this somewhere. If I wanted to test this systematically, what I would do is I would get some animals, and I would, maybe I wouldn't just get myself. I'd get some groups of men and get them to keep a diary of their testicular injuries over a period of time, and then we could compare them. We could see, are there more testicular injuries if you have a cat as a pet, for example, compared to a dog, compared to a bird. So we've taken these men whose testicles, because we've randomised, are a random sample of the testicles in the world, something. And so we've given some of them cats to go and live with for a week. We've given some of them dogs to go and live with for a week, and we've given some of them birds. And they're keeping a record of pain or something like that. So we've got more than two conditions here that we need to compare. So this is the kind of situation where we're expanding from last week. We've got a more complicated situation. And of course, we may have had other animals. Maybe we had ducks. Ducks are birds, aren't they? Maybe we had lizards as well. So we thought, let's get a lizard into the mix. I don't know why we'd have a hypothesis about lizards, but there you go. So we could have some lizards in there and maybe a fish or something. I can't imagine what fish would. Maybe they'd beat your testicles with their fins or something, but probably only if you stuck them in the fish tank. So you could expand this. You could have lots and lots of groups. So the models we're fitting are going to get more complicated. So you might argue, well, why can't we just keep this simple and just do so we know that we can do a comparison between two groups using a linear model. Why don't we just sort of do that lots and lots of times? So compare cats and dogs, and then quite separately compare cats and birds, and then separately compare birds and dogs. The reason we don't do that is because of the whole significance testing thing that we do. So when we apply tests, statistical tests, we have this p-value of 0.05. So that's our criterion for accepting significance. And although we've looked a little bit that that's not a perfect process, but nevertheless it tends to be adopted. If you do lots and lots of tests on the same data, basically those probability values kind of accumulate, if you like. So the reason we use the 0.05 level is it's kind of a 5% error rate. So by using 0.05, we're saying we should only make a mistake 5% of the time. And by make a mistake, we mean accept something as being significant when in reality it's not. If we do lots and lots of tests on the same data, sort of around the same hypothesis, then those errors add up. So suddenly it's not a 5% rate, it's a 5% for every test that you do. So if we had, say, dogs, cats and birds, we'd have a 5% chance of making an error when we compared dogs and cats, a 5% chance of making an error when we compared dogs and birds, and a 5% chance of making an error when we compare cats and birds. So across the general hypothesis we wanted to test was, there are differences between the animals. So by doing 3 tests within that sort of overarching hypothesis, we've now got like 3 lots of 5% chance of making an error. Now, if you want to get technical about it, you can work out how those errors add up using this equation. You don't ever necessarily need to do that. So this is the 0.95 is sort of, it's the 5% error flipped on its head, basically. So it's the probability of not making an error. And you have to you sort of power it. So that's to the power of n, where n is the number of tests that you've done. So we've done 3 different tests here. So if we did 0.05 to the power of n and then subtract it from 1, you'd work out basically that there's about a 14% error rate. So we started off wanting, ideally, to have a 5% error rate. That's what we use, that's what we accept as being sufficiently small that we can kind of go ahead and do what we're doing. But if we do lots and lots of tests around the same hypothesis, that's accumulating up. So we would now, with 3 tests, have a 14% error, which is unacceptable. We want it to be 5%, not 14. Let's imagine we had 10 groups rather than 3. Then if you sort of plug this into here, you'd end up with something like a 40% chance that one of those tests would make an error, which again is it's way, way above the 5% threshold that we like. So we've got to come up, we can't just sort of do these individual little linear models. We have to come up with like a linear model that sort of includes everything relating to the hypothesis that we want to test. So what's the difference between experiments and correlations in terms of the linear model? So as I said, we've seen ANOVA before when we've done what you might call regression, when we've looked at sort of naturalistically measured variables, and we've seen that ANOVA is used to test whether the linear model is a good fit of the data. In other words, are the predictors we've put in sort of good at predicting the outcome in a general sense? When we've done experiments, actually we can use the linear model in exactly the same way. So the ANOVA, or the F ratio, still tests whether the linear model is good at predicting an outcome. So whether the predictors we've put in are kind of a significant fit of the outcome variable. The big difference is what that linear model looks like, or what it represents. Because when we've done experiments, what that linear model represents is our experimental manipulation. So as we saw last week, you can set up a linear model where the predictor variables represent kind of differences between means. So in experimental conditions, situations, that's what we're doing. We're setting up a linear model that compares the different means of the different conditions that we've manipulated. So the point I'm trying to make here is the kind of the maths, or the model we're fitting, doesn't actually change at all. We're doing exactly the same thing that we were doing a couple of weeks ago in your practical classes. Nothing has changed. So everything going on in the background is exactly the same. The only thing that's changed is kind of what the model looks like, so what those predictor variables represent. And when we've done experiments, those predictor variables represent differences between means rather than kind of variation in scores on a naturally occurring variable. So the ANOVA that you've already come across in a table in your regression outputs is essentially the same thing as the ANOVA we're now talking about in the context of experiments. It's not different in any way, shape or form. It's asking exactly the same question. The only thing that's changed is the way that what the model is, essentially. So just to remind you from last week, this is a slide I put up then. So this is comparing goals scored in Asian elephants and African elephants. And we saw when we compare two means, our linear model looks like this. It's just looking at the mean in one group and the mean in the other group, and the sort of the gradient or the beta value for the predictor is the gradient of that line, which is the difference between the two means. So our linear model is going to look at differences between means when we have different groups of variables like we do, different groups of people like we do in experiments. Now, when we've used ANOVA before, again, just because we have looked at the F ratio very briefly, so this is just a bit of revision, I use the analogy of cutting up a cake. So if you imagine this rather than... Actually, I've just realised this is slightly Halloween themed because it's a pumpkin cheesecake. Hurrah. So this is a big cake, and this cake represents the variability in our outcome score. So that's sort of the thing we're trying to predict. So if you have the cake as a whole, that's basically your total variability in your outcome variable. So if your outcome variable was testicular injuries, that's how much variability you have in testicular injuries. And we've seen in previous lectures that you can sort of summarize that using a total sum of squares. And then we saw that you can fit a model, and then basically you sort of divide this cheesecake up into two bits. So one bit of it will represent the improvement due to fitting the model. So how much better you are at predicting the outcome as a result of fitting a linear model. That's represented by the model sum of squares. And you're left over with some error, because no models are perfect. So you can work out the sum of squares, the residual sum of squares, which is basically how much error in prediction there is. And your F ratio is, although we skipped over this a bit when we covered it in regression, it is essentially the ratio between your model and your residual. So it's the ratio of how much improvement there is due to fitting your model, how much better you are at predicting things as a result of fitting your model, against how much error there's left over. So essentially it's a signal to noise ratio. It's how good is my model relative to how bad it is. Now the thing I skipped over a bit is the fact that we don't use sums of squares, we use mean squares. So this is, going right back to the beginning of the module, mean squares are just average sums of squares. So when we looked at sums of squares at the very beginning of the module, we said, well, they're dependent on how many scores you've used, because they're a total. So the more scores you have, the bigger your sums of squares will be. So sometimes it's useful to take an average sum of squares. So that gives you a sort of a measure of variability that's independent of how many scores you calculate, how many scores you've used to calculate it. So the F ratio uses these mean squares, which we'll come on to in a minute. But I just want to remind you really of what we already know about the F ratio or about ANOVA. So in the context of regression, or regression using sort of naturally occurring predictors that you've measured, this is what we've seen so far. Now when we do experiments, nothing really changes. We still have a model sum of squares, we still have a total sum of squares, we still have a residual sum of squares. All that changes is what the model looks like. So we're really just, like I said, we're kind of going over old ground. So the theory of ANOVA in the context of experiments is exactly the same as it is in the context of regression. So we can calculate how much variability there is in our outcome variable. That's the total sum of squares. We can divide that sum of squares into two. So one thing we want to know is how much variability is explained by the model we fit to the data. So in other words, when we fit a linear model, how much better does our ability to predict the outcome become? And we quantify that using a model sum of squares. And we'll also always have some error. So there'll be some variability that can't be explained. There'll be some error in prediction, and that's quantified using a residual sum of squares. So same three sums of squares that we've already dealt with before. And the F ratio is simply the ratio of the model sum of squares to the error. So in other words, like I said, it's a signal to noise. It's how much variability is explained by the model, how much does our prediction improve, against how much error there is left over. Now, if you want to think about this in terms of experimental manipulation of variables and all that sort of thing, you're basically comparing the ratio of of what effect your experiments had, that's at the top half of the F ratio, against individual differences, because in psychology most of the error we have will just come from individual differences. So again, just think of it as like it's a signal to noise ratio of sort of how successful the experiment's been against the background noise of, you know, sort of differences you'd get because people are different. Basically, if that F ratio is big, if the experiment's had a big effect relative to the amount of sort of noise or error in the data, then you'll say it's, you know, you'll get a significant F ratio, and your conclusion will be that your experimental manipulation has kind of been successful. Because bearing in mind, the F ratio is kind of weighing up how much your predictions improved as a result of fitting the model, and the model is representing your experimental manipulation. So the F ratio is basically telling us how successful has the experiment been relative to the sort of naturally occurring variability in the people that we've tested. So if your F is significant, basically means your model is a significant fit. In the context of experiments, it means there are differences between the groups. Your manipulation has been successful, for want of a better word. So the example in the textbook, which we're going to focus on a bit now and also next week, was to do with, at the time I was writing the first edition of the textbook, there was loads of, I get lots of examples from newspapers, and there was loads of stuff in the newspapers about Viagra. There's not very much about it in the newspapers now. There's quite a lot of it in my inbox sometimes, but it's, you know, it's not such a exciting thing. But at the time, there were loads of journalists like taking Viagra and then writing their stories about it, and, you know, my weekend on Viagra, and some of them were quite unpleasant to read, really. I mean, no one wants to read about a journalist with a hard-on for 3 days. But anyway, fortunately that trend has died down. So the example was inspired by that. So what's the effect of Viagra? Now in the psychology literature, so we sort of know the effect that Viagra has on, you know, well, physically we know what effect it has. But in the psychology literature, there's been a bit of a link between the sort of physicality of the sexual response and your sort of psychological libido, if you like. So the example is kind of based around not looking at the effect of Viagra on physiology, but looking at the effect of taking Viagra on your actual desire to have sex. So we have 3 groups: the placebo group, who were given a sugar pill, so they may have thought they were taking Viagra, but they weren't. And then we have 2 different doses of Viagra. And I've just, to keep things simple, called them a low dose and a high dose, because that allowed me to avoid the issue of actually having to work out what a dose of Viagra would be, because I don't have a clue. So the outcome variable, or our dependent variable, if you want to use that terminology, was some kind of measure of libido. So let's say like a self-report, some kind of psychological thing. So these are the data. The samples are, I kept them really small in this example because in the textbook I go through everything by hand, and if you have big data sets that becomes a bit complicated. So we've just got 5 participants in each group. So there were 5 in the placebo condition, and these are their libido scores. 5 in the low dose condition, that's their libido scores, and 5 in the high dose condition, and that's their libido scores. Now, things well, like I say, we don't really go through the calculations in this lecture. If you're interested, it's all in the textbook. But the main thing to focus on here are the means of the 3 groups. So what we're kind of saying is, if we took a random sample of men and split them into 3 random groups, we'd expect that these libido scores ought to be pretty similar amongst those 3 groups. So on balance, you shouldn't get too much difference. So the model we're fitting is really testing whether the values that we're getting for these means are different because essentially we've done something different to these 3 groups. So our model is going to represent our experimental manipulation. It's going to represent the fact that we've given some people placebo pills, we've given some a high dose and some a low dose. So, if you want to fit a linear model with multiple groups, we touched on this a bit last week. Now, there's a very important distinction here between what you kind of actually do in SPSS and what I'm going to talk about here. So in SPSS, what you do is you go to the ANOVA menu and you run an ANOVA. You don't go to the regression menu and run it through that. That is important to point out because people, because of the way I teach the theory, it becomes a bit confusing for some people that we don't do everything through the regression menu. But really, the reason we don't is SPSS is trying to make your life easy. So it's trying to sort of take out the ANOVA stuff into a different menu so that you know, like, when I'm doing an experiment, I just go to this sort of ANOVA type menu. But I think in the menus you'll notice that things tend to be labelled GLM, and that stands for General Linear Model. So it is doing, behind the scenes, it's doing a linear model. It's just putting things in a different menu to try and make life a bit more straightforward for you. So what I'm talking about here, you don't actually do. SPSS does this for you. But we saw last week that we can use what are known as dummy variables to code whether a participant is in a particular group or another. So like with our Asian and African elephants last week, we used a 0 and 1 coding. So 0, I think, was Asian elephants and 1 was African elephants. We can use the same principle here. We can choose a control condition, which will self-evidently be our placebo group. And in most experiments, you have a control group that you've specifically designed to be a control group. So we would have that control group and we would code those with zeros, or this is what SPSS is doing behind the scenes. So it codes those with zeros, and then it codes the other groups with ones. And the way it would need to do that, if you have 3 groups like we have here, so we've got high dose, low dose, placebo, you need to code it into 2 dummy variables. Like I said, we did touch on this last week. So you'd have a dummy variable and a second dummy variable. Dummy variables are just zeros and ones in a column. Like I said, SPSS is doing this for you. You don't have to input any of this. I'm just telling you for the fun of it. So your placebo group, it's a baseline, so it gets coded as 0 for both dummy variables. And then what it does is it codes in one of the dummy variables, it will code one of the groups with a 1. So in this dummy variable, it's coded as high dose as 1, and in the second dummy variable, it codes the other group as 1. So this is high dose 1, everything else 0. This is low dose 1, everything else 0. Now, because placebo is the only group that is 0 across both dummy variables, what that effectively does is it makes it the sort of baseline against which everything else is compared. So the important thing is when SPSS is doing this, is it will put both of these variables into the linear model at the same time. That's absolutely vital. So it does like a forced entry thing. It puts them both in simultaneously. And in doing that, by having both of these variables included as predictors at the same time, basically your placebo ends up being a baseline. So effectively, the linear model we're fitting will look something like this. So it's libido predicted from, obviously we always have this kind of intercept, so this is the value of the outcome when both dummy variables are 0, so that will be the mean of the placebo group. And then it's predicted from dummy variable 1 and dummy variable 2. Now what those dummy variables represent, the first one, because we've coded high dose as 1, it represents the difference between the means of high dose and placebo. Whereas dummy 2, because the low dose group is coded as 1, it represents the difference between the means of the low dose group and the control, in this case the placebo. So the placebo is acting, because it's 0 in both of these columns, it's acting as a baseline in each dummy variable. So basically this is the linear model we're fitting. I'm just putting that up there to demonstrate that it is still a linear model. I'm not kind of trying to trick you or whatever. It's just exactly the same as everything else we've dealt with on the whole of this module. So we're just predicting an outcome based on predictor variables. It's just that these predictor variables represent means. So the model looks a bit like this. So here are our placebo group, here are our low dose group, the blue squares, and the triangles are our high dose group. These bars are the group means. And I'm just going to circle the groups so that you're really, really aware that these are different groups of people. The model we're fitting to the data are basically those 3 means. So the linear model, that dummy coding that I just tried to explain, is representing differences between these 2 means. So one of the betas will represent, well, because we picked this as a baseline, one of the betas will represent the difference between those 2 means, and the other beta will represent the difference between the high dose and the placebo. So although it's not a linear sense it's not a linear model in the sense that we can look at it as a sort of straight line, it's the same model. Nothing is changing at all, apart from kind of what it looks like, because it doesn't look like a straight line anymore. It looks like 3 different means, because that's what it is. So how do we quantify whether prediction based on those three group means improves our ability to predict libido? Well, we use the same sums of squares as we've used before. So I've put up a similar diagram before when we first looked at the linear model. And we can first of all work out how much variability there is in all of the scores. So what we can do is we can fit, if you remember back to when we talked about the linear model, we fit the overall mean of the data. So the grand mean of all libido scores. And so there it is, grand mean. And these things are the deviations. So they're the differences between each score and the overall mean of all scores. So hopefully this might be slightly familiar. And to get sum of squares, we simply add up these deviations, but we have to square them because some of them are below the line, some of them are above the line. So when I first introduced sums of squares, I said, well, we're coming back to this time and time again, and lo and behold, we are. So if we want to know the total variability in libido scores, we simply fit the mean of all the scores and work out how much error there is, if you like, so how much squared error there is between all the data points and the grand mean. That's all there is to it. So that's the first thing SPSS will do. So that's the total variability. If you happen to want to represent this as an equation, it will look like this. This just means you take each score, so you take the score from individual I, so this could be like score of Barry, and from that you subtract the grand mean, so the mean of all scores, and then we square them, and we do that for every single person and add them up. That's all that equation is just the previous diagram in the form of an equation. Turns out for these data you get a score of about 44. Hello.
How does this relate to sum of squared errors that we did at the beginning? Is this just another term?
No, it's exactly the same.
So it's just another way of representing the same.
Yeah. So when we did sum of squared errors in the context of variance, this is exactly the same. We treat the data set as a whole and basically compute the same sum of squares. Or SPSS computes it for us. Now, the thing is, I talked about at some point we're going to look at average sums of squares. So how do we sort of work out those averages? Well, we end up using what are known as degrees of freedom. So basically, degrees of freedom are, because we're using samples to estimate populations, degrees of freedom are normally one less than the sort of number of scores or the number of things that we've used to compute a sum of squares. So this is because if for example you're estimating the mean in the population, you have a sample, your sample mean say 10, you assume that your population mean is 10 as well. You don't know for a fact that it is, you just assume that it is. So you fix the population mean at 10. So what that means is that the scores, if you like, within the population will have to be such that that mean is 10. So whatever those scores are, they have to end up having a mean of 10 because that's what you've assumed the mean is. So basically all the scores in the population can be whatever they like apart from the very last score. And that last score will have to be a value that brings the mean to 10 because that's what we've assumed the population mean is. So it's a bit like when you're playing sport. So if you imagine you had, say, a soccer team, and so you've got 11 positions on the pitch. When the first person turns up to play, you can choose whatever position they want to go in. So you can say, right, you be the goalkeeper today. When the second person turns up, you've still got 10 positions. You've still got freedom to choose where they go. So you could say, right, you be the left back today. Third person turns up, you've still got lots and lots of freedom. You go, well, you be the left wing today. So on and so forth. So more and more people turn up, you plop them into the team. Now at some point you'll have 10 positions on the pitch already filled. There'll only be one position left. So when the 11th person turns up and says, okay boss, where do you want me to play today? You have no degrees of freedom over where they play. You've already occupied all the other places in the team. They will have to play in that final spot. That's basically kind of what degrees of freedom is all about. So degrees of freedom are normally like one less, or degrees of freedom associated with sums of squares are normally one less than the number of scores that you've used to calculate the sum of squares. So in the case of the total sum of squares, our total number of scores was 15, which means our degrees of freedom are 14. Now, if none of that made any sense, I wouldn't worry, because no one really actually understands degrees of freedom. It's an incredibly slippery concept. It's very difficult to explain. That's pretty much the best I can do, I'm afraid. Maybe I should do a whole lecture on it, but I think people might get suicidal if I do that. Anyway, main thing to hang on to is normally one less than the number of things you've used to compute the sum of squares. So what about our model sum of squares? Well, like I said, our model are these free means. It's not a straight line anymore. This is the model. So for each group, our prediction is the mean of that group. If you say, what do you reckon the libido scores were for John? You say, well, what group was John in? You say, well, John was in a placebo group. You go, well, okay, on balance, his score is likely to be the mean of that group, which I can't remember what it was anymore. So this is our model. And this line here is just to show you again the grand mean. So the question the sum of squares for the model is asking is how much better are we at predicting the outcome using the group means relative to using the grand mean. So again, this is a very similar diagram to one I've put up before. So what we're saying is for each participant, what's the difference between the prediction we make based on their group membership and the prediction we make based on just using the overall mean of everyone. So for participant 1, our overall prediction is 3 point something or other. So that's if we ignored their group membership, that's what we predict. If we include their group membership, then we predict this value. So it's the difference between the two. Now, as you can see, for this person, actually the overall means a slightly better prediction of their score than the group mean. But for many others, like this chap, the group means a much better predictor than the overall mean, and for these chaps, the group means a better predictor than the overall mean, so on and so forth. But essentially, we're just looking at the difference. What's the difference between using the group mean? What's the difference between using our model as a predictor versus using the overall thing, the overall mean? So what we're effectively doing is saying for each participant, what's the difference between the group mean, so the mean of the group they're in, and the overall mean? Now, in equation form, that will be represented by like this, just like I say, just so you're aware. So this is saying for participant I, so for an individual, say John, you say, well, what's the mean of the group that John was in? What's the mean overall? And you take the difference between those two. Now, because there's more than one person in a group, we just multiply by the number of people in a particular group. So what we're saying is, you take the mean of the placebo group, subtract it from the overall mean of all the scores, square it, and then times it by the number of people that were in that group. And obviously, you do that for each group. So you kind of add it up for each group. So we end up here with a value of around 20. So bearing in mind, we started off with about 44 units of variation to explain, and our model can explain about 20 of them. In terms of degrees of freedom, well, what did we use to compute our sums of squares? Well, we used the group means, and there were three group means. So it becomes 3 minus 1, which is 2. So it's 1 less than the number of group means that we had. K is normally used to represent the number of groups, so you'll see K a lot in that context. So we've got a sum of squares of 20, and that was based on using sort of two degrees of freedom are associated with that. So if we want to work out what the average variability is rather than the total, we simply divide the sum of squares by the degrees of freedom. So the degrees of freedom tells us something about the number of scores that we used to compute the sums of squares. So if we want a sort of average, we're just taking a total and dividing by the number of scores, sort of, that we used. So our average sum of squares, our mean squares for the model is just the sum of squares, which was about 20 divided by the degrees of freedom, which was 2, which means 10. So we've got about 10 units on average that can be explained by the model. What about the error that's left over? Well, so we've got our grand mean, we've got our group memberships. The error left over is going to be the difference between what we predicted for each person, so their group mean, and the score that they actually got. Now, this should look very, very familiar, because this exactly is what you do when you work out like the sum of squares around a mean, or the variance or even standard deviation within a group. And that is exactly what SPSS will be doing. It works out the variance within a group. So it does it first for the placebo group. And that means for the placebo group there will be 4 degrees of freedom, because that sum of squares is based on 5 scores. So the degrees of freedom is 1 less than that, 4. It then does it for the low dose group. So this is just literally working out what the variance is within the low dose group. So what the individual differences are. Again, that will be based on 4 degrees of freedom. And then it does the same for the high dose group. So again, it's just looking really at the variance within the high dose group. And again, because there's 5 scores there, that has 4 degrees of freedom. And then it adds them up. So it works out the sort of sum of squares within this group, sum of squares within this group, sum of squares within this group, and then it adds them all up. And because there are 4 degrees of freedom associated with each sum of squares, it adds them up too. So we'll end up with 12 degrees of freedom. Now in equation form, this looks bloody hideous, to be perfectly honest, which is why I prefer to sort of explain it with diagrams, because I think they're easier to understand. But essentially what this is saying is you work out the sum of squares within each group, and then you sort of add what you get for the different groups up. So it's a bit like saying you work out the variance within a group and times it by the number, or times it by the degrees of freedom effectively, and then you add that up for the groups that you have. But like I said, if the equations don't make sense, that doesn't particularly matter. What's more important is that the diagram and the conceptual understanding makes sense. So what we're doing here is working out the variability within groups. So we end up with 23.6 units. As I said, we've got degrees of freedom within each group. So degrees of freedom for the placebo, for the high dose and the low dose. And there were 5 scores in each group, so we end up with 4 and 4 and 4, which gives us 12. So that's what's going on behind the scenes, which is the same as what's going on behind the scenes in any kind of regression. To work out a mean square, again, we take the sum of squares and divide by the degrees of freedom. So we had 23 total units of variation, but they were based on 12 degrees of freedom. So we get a much smaller average sum of squares. So this is, around about 2. So looking at our cake again, I just want to point out that our model sum of squares and our residual sum of squares, they're 2 bits of cake, so they should add up to the total sum of squares. So if we put these values that we've just computed in, our model sum of squares was 20.14, our error left over sum of squares was 23.6. When you add them together, you do get the total sum of squares, so the variability amongst all scores. That works with the degrees of freedom as well, which I thought was on that slide, but it's not. So you can add the degrees of freedom. You've got 2 for the model, 12 for the residual, and that gives you 14, which was what we had for the total. So the F ratio is just how much the model fits the data based relative to how much error there is. So I've said all this before. In the case of experiments, what this F ratio is representing is the difference between means. So it's going to be the ratio of the experimental effect against the background error. So it's a signal to noise ratio. How good is my experiment compared to how much error there is? In linear model terms, it's how much better are we at predicting the outcome based on group means compared to predicting the outcome, compared to how much error there is when we predict the outcome based on group means. So it's how good our prediction is from group means relative to how bad our prediction is based on group means. So it's just this ratio here of model sum of squares against residual sum of squares. So, mean squares. The model mean squares relative to the residual mean squares. So how good the model is compared to how bad it is. In this case, we end up with an F ratio of around 5. And basically, you can compute a probability. So what is the likelihood of getting an F value as big as 5.12 if there's no effect? So if the means of the 3 groups in reality ought to be equal. So in SPSS, you end up with this table, which you will have seen before. The sums of squares that we've just computed for the model, the error, and the total. The degrees of freedom associated with each one. And the model sum of squares, which you can compute from these 2 things. So 20.14 divided by 2 gives us 10. you'll have the F ratio and you'll have a p-value. And like I said, if this p-value is less than 0.05, then that basically means you say it's a significant effect. In other words, predicting our outcome based on group means is significantly better than not doing that. So in other words, our group means are significantly different. What we don't know at this stage, and what we're going to cover in an additional lecture that's next Wednesday, is how we then find out which groups are different from which. So is it the high-dose group that's different from the placebo or whatever? So this is only telling us overall that group means are different. And we would report, for example, report the effect in a very general way, therefore. So the dose of Viagra had a significant effect. We're not saying which groups differ, just it had a significant effect on levels of libido. We report an F. We report the model and the residual degrees of freedom, the value of F, and an exact p-value, unless the p is very, very small, and then you can use less than 0.001. But other things, generally, exact p-values are good things to report. So that's it. I know that was a lot to take in, quite dense and everything like that, but like I say, the main things are to try to understand conceptually what the sums of squares and the mean squares and the F represent, and to try to relate what's in this lecture back to the lecture that we originally had on the linear model, where we first talked about these sums of squares and so on and so forth.